Let's suppose that we have a 10 microcoulomb positive charge here and a negative 14 microcoulomb charge here, and they are 20 centimeters apart. And 5 centimeters between them from Q1, we will say there's our test charge right there. And we want to know what is the electric field at that point? And if the test charge was 6 microcoulombs, what would the force be? So let's solve that. So what I think you ought to do is, okay, it sounds kind of weird. I think you should draw the free body diagram of the test charge. Well, so here's your positive charge. Here's your negative charge. You put your test charge here, and then you say, you look at them separately, and you say, okay, what is Q1 going to do to my positive test charge? It's going to push it in what direction? To the right. To the right, to the right. And then, what about this one, though? This is negatively charged. So shouldn't it push it in the opposite direction? That's a mistake a lot of students will make. Actually, this positive test charge is attracted to this. So the electric field is going to be the sum of the electric fields that would have been produced by each of these individually, and they're both in the same direction. They're both in the positive I hat direction. So let's figure out what E1 is. And you go, okay, K Q1 over R1 squared. And that's, what is that? That's going to be 8.99 times 10 to the 9 Newton meters squared per coulomb squared times 10 microcoulombs. Remember when you use your calculator to put in times 10 to the negative 6. The nice thing about the micro symbol is you don't have to write that down every time. It's just a shortcut. And then over R1 squared, and that's 5 centimeters, so 0.05 meters squared. And then you say, okay, in the R hat direction. Okay, R hat direction. So you evaluate that. This times this divided by this squared. And you get a magnitude, at least I did, of 3.6 times 10 to the 7 newtons per coulomb. Now, what does R hat mean? Now you have to look at the problem and decide what direction it's actually in. And I'm going to say, oh, here's E1 right here. It's in the I hat direction. Now let's figure out what E2 is. It's, K Q2 over R2 squared. And that's equal to 8.99 times 10 to the 9 Newton meters squared per coulomb squared times negative 14 microcoulombs. And then you have R2, and so if this is 20, this is 5, so this is 15, or 0.15 meters. And you square that. And now you get, this is what I got. I got 5.6 times 10 to the 6 newtons per coulomb. Now let's talk about direction. Because students get, you guys, it's easy to get confused if you stop thinking about what's physically actually happening. What does this negative mean? Well, the negative really should be attached to, and I didn't put it in there, an R hat vector. So you have a negative, so this should be negative R hat. So when you see that, when you multiply by a negative charge, and this is true for Coulomb's law as well as this electric field thing, If you see the negative there, you go, oh, okay, that negative means it's an attractive force between my test charge and this charge over here. Well, what direction is attractive? I hat. So there's no just like automatic mathematical black box you just crunch it into. You have to look at the problem and say, what direction is that test charge being pulled in? And put that correct direction there. The mistake students make on a problem like this, that you might see in a couple of days, is they put a negative sign here because there was a negative charge. And then they try adding them together. They try adding them together as scalars, and you get the wrong answer. So now it's just the overall electric field is just E1 plus E2. And so you're going to add this plus this, and when you do, you get 4.26 times 10 to the 7 newtons per coulomb in the I hat direction. Did you all get the same thing? Okay. Now to find the force on my test charge, what if my test charge is equal to 6 microcoulombs? Well, the force is just equal to the charge times the electric field. So this is going to be 6 microcoulombs times 4.26 times 10 to the 7 newtons per coulomb in the I hat direction. And remember that 10 to the negative 6. And when you do, you will get a force on my test charge of 256 newtons in the I hat direction. That's a lot of force. Yeah, electric forces are very powerful, even given a small amount of charge. So there's my answer. Yes?
I know it doesn't make that much of a difference, but I got 4.16 and if you went salt with it.
You got 4 point what?
16.
Did I add it wrong when I? Could be. I worked this out ahead of time so that I wouldn't have this issue, and then look what happened. So you got 3.6 times 10 to the 7, is that right? Plus 5.6 times 10 to the 6 equals, oh, it's 4.16, you're right. And I think I must have just written it down wrong when I worked this problem out ahead of time. And then, does that change this answer? So I did carry that mistake forward. So, what is it? What do you get? 6 times 4.16. So you get 249, right? 200 or 250. If you round it off to 3 significant figures. Okay, sorry about that. But the big idea here behind this problem is that when you have two point charges and you're trying to find, what's the electric field, you have to add them together, but you really have to be careful about what direction each charge is pulling on your test charge, and then write it down appropriately. Yes?
But what happens to the microcoulombs?
Oh, they got multiplied in. This is times 10 to the negative 6 with 10 to the 7, that's 10. So 6 times 4 times 10 is 250.
But in the first part for the electric field.
Up here? Right here?
Yeah.
Didn't I think I did multiply by 10 to the negative 6. I think this is right. Yeah. I don't write down times 10 to the negative 6 when I'm doing the problem. I just type it down in the calculator though. Okay. That is all.